If you haven't already, read chapters 12 and 13 in your textbook before starting this lesson. So what is a composite material? Well, one definition of the word composite is a thing made up of several parts or elements. For our purposes, a composite is a material comprising two distinct phases that are mechanically bonded together. Note that the word comprising means that other things may be present. So one could say that a composite has two distinct phases and may include other things. Well, why do we need two parts, elements, or phases? Well, we need a composite when a single homogeneous material cannot provide the properties that we need. In general, the two phases are the reinforcement, which provides strength, and the matrix, which bonds the reinforcement elements together and provides form to the material. There are a variety of composite materials classified by the type of matrix. Polymer matrix composites have matrices that are made of polymers or plastics. Metal matrix composites have matrices that are metallic. Ceramic matrix composites have ceramic materials as their matrices. Carbon-carbon composites have matrices of carbon, and the reinforcements are made of carbon as well. We'll focus on polymer matrix composites for now. The most common reinforcement form is the fiber. A fiber is made up of usually thousands of individual filaments. Hundreds of fibers are bundled into roving or tows. Reinforcements are usually made from high-strength, brittle materials. Reinforcements are specified by the material type and the strength or stiffness properties. Coatings, called sizings, are applied to fibers to improve adhesion between the matrix and the fibers. One key to a well-performing composite is how well the matrix adheres to the fibers, because one function of the matrix is to transfer the load between fibers. Reinforcements in composite materials can take on many forms. The fibers can be long, usually spanning across a composite part. They can be aligned, all oriented in substantially the same direction, or unaligned. If not continuous, they are discontinuous, shorter fibers that only span a certain distance. Very short fibers are called whiskers. Particulate reinforcements can also be used. As a general rule, the longer the fiber, the stronger the composite part for the same matrix reinforcement combination. Composite materials can be woven into fabrics, much like the shirt you're probably wearing. Glass fibers are a very popular reinforcement. The overwhelming majority of glass fiber reinforcements are made from electrical glass, or E-glass. S-glass has higher strength and elastic moduli, but is much more expensive. The difference between the two glasses is in the composition. Another great reinforcement is carbon or graphite. Graphite is a form of carbon. Graphite is carbon, but not all carbon is graphite. The terms are used interchangeably today, but there is a difference. Both start from a precursor material, usually pitch, a tar-like substance, or polyacrylonitrile, PAN, which is a synthetic polymer. In either case, the precursor material is drawn into fibers and heated to remove, quote, all elements other than carbon. The carbon fiber is then heated to about 2,400 degrees Fahrenheit, which produces a product that is about 93 to 95% carbon. Graphite fiber is heated to about 3450 F to 4500 F, also to remove all other elements than carbon. The higher temperature is more efficient in removing these tramp elements, which produces a fiber that is more than 99% carbon. Carbon fibers are typically very small. The photograph shows two fibers. The light colored one is a human hair, and the other is a carbon fiber. The mechanical properties for metals and neat or unreinforced plastics are considered to be isotropic, the same in all directions. Composites inherently have different properties in different directions because of the directional properties of the reinforcements. Composite materials can be quasi-isotropic or nearly isotropic if the reinforcements are randomly oriented and dispersed in the matrix at a uniform density. The other difference between composites and unreinforced materials is ductility and brittleness. In metals, and in plastics for that matter, a lack of ductility means the material is brittle. This is not the case in composites. Most composite materials are not ductile, but they do not experience brittle fracture as a result of fast-moving cracking. Composite materials are not a silver bullet. They are not the solution to all problems, but they do have characteristics that are very desirable, if not essential, to many designs. With regard to static mechanical properties, they have higher strengths, higher moduli of elasticity, and lower densities than comparable unreinforced materials. We use the term specific strength, the material's strength divided by its density, and the specific stiffness, the material's modulus of elasticity divided by its density, to describe strength and stiffness to weight characteristics of materials. Composite materials often have lower coefficients of thermal expansion than their unreinforced counterparts. They also typically have greater resistances to fatigue, creep, and wear than their unreinforced counterparts. They can also be formulated and designed to have a range of electrical and thermal conductivities. As previously mentioned, composites are known for their strength and stiffness to weight characteristics. This chart shows a comparison of various unreinforced materials and composite materials win. The specific tensile strength is on the vertical axis, and the specific stiffness or modulus is on the horizontal axis. The highlighted box shows where steel, titanium, magnesium, and aluminum fall. These lines show the characteristics of various carbon, glass, and aramid reinforced epoxy composites. Note that UHS means ultra high strength carbon fibers, and UHM means ultra high modulus carbon fibers. There are many other reinforcement materials. Aramid, you know this material by its trade name, Kevlar. High density polyethylene and basalt, a rock that can be melted and spun into fibers, are used in polymer matrix composites. The others are typically used in composite materials having other types of matrices. Matrices of most polymer matrix composites are made from thermosetting polymers. These are some of the polymers that are used. Advanced polymers that are used in products requiring higher strengths or higher service temperatures. Engineering polymers are used in more commercial products. There are thermoplastic matrices used in some composite materials. The ones shown on this chart are some of the more popular ones. Common reinforcements are fibers made from carbon, glass, and aramid, or Kevlar. Metal matrix composites have matrices that are metallic. Aluminum is often used. Common reinforcements are short fibers made from ceramic, like silicon carbide. Ceramic matrix composites have ceramic materials as their matrices, such as carbon, silicon carbide, alumina, and mullite. Their reinforcements are often made from the same material, but in short fiber form. Carbon-carbon composites have matrices of carbon and are considered by some as a subclass of ceramic matrix composites. Both the matrix and the reinforcement are made from carbon. These are used in hot environments, like the heat protection panels for the space shuttle. Composite materials provide some real benefits to manufacturing, but they are not the answer to all problems. They do, however, allow large, complex shapes to be made with fewer parts, which typically reduce costs. They can be molded in ways so that little machining is required to produce a finished product. In the aircraft industry, composite materials allow smooth, repeatable contours to be produced. This is an example of a carbon epoxy composite part as it's being manufactured. This is part of the fuselage of the Boeing 787 Dreamliner. The interior of the part, indicated by the arrow in the large picture, is shown in the small picture. All of the skin structure is essentially one piece, a monocoque construction. The hat stiffeners, indicated by the yellow arrow, are co-cured with the skin. Separate parts are assembled and cured together to produce a single part. When you're comfortable with the material, take the quiz for this lesson.